The Rock Whisperer. Do you hear the earth talking to you?
Welcome to video 4-3, and in this section we're going to be talking about ellipses and eccentricity. So what we need to know about ellipses or eccentricity, that there are three laws that were invented by a scientist named Johannes Kepler. Johannes Kepler lived from 1571 to 1630, so quite a while ago. He was a mathematician, he was an astronomer, and he was also an astrologer. And at that particular time, astronomy and astrology were kind of all together, where astronomy is the study of the sky and astrology is the study of what sign are you, what zodiac sign. So his major contribution to science, or one of his major contributions I should say, were the three laws that he came up with. And I'll have diagrams as we go along to indicate these. The first two are key that we need to know. The third one, it's good to know what it is, but we will not be tested on that. So, law number one. Law number one. The orbit of planets are ellipses, and the sun is at one focus point at the ellipse. So when you talk about a circle, you have a center point. There's actually 2 points at the center. With an ellipse, there are 2 different points, and we create the elliptical shape around that. So the sun would be at one point, the other is an imaginary point in space. The second law that he came up with was that a line joining the planet to the sun, they sweep out equal areas over equal time. So look at the diagram that you see here. You can see that on one side we have a large section, or it appears to be larger, and on the other side it seems to be a narrower section. If we calculate the area for both of those sections, they're going to be the same thing. That means we're traveling a greater distance in the same amount of time, which means we're going quicker or we're going faster. Planets always travel faster when they're closest to the sun because of more gravitational attraction, and when they're further away on the side that has a shorter distance, then we can realize that that planet is going slower, and that's when we're further away from the sun. And the third law that he has is the ratio of the square of the revolution periods for 2 planets is equal to the ratio of the cube of the semi-major axis. It's a mouthful, and there's also a diagram here that shows it, and there's a mathematical formula that goes along with that. We won't be applying that one, but we do need to know that he had 3 laws, and that is the third one. So when we talk about eccentricity, we're talking about how flat or how elongated an ellipse. When we talk about a perfect circle, we look at the circle and we can calculate the eccentricity. There's no difference between the 2 points in the middle, so therefore our eccentricity is going to be 0. If we have a straight line, the length of the major axis is the same as the distance between the foci points, the focus points, and therefore it's going to be 1. So the more elliptical, the more stretched it gets, the closer to 1. The rounder it is, or the closer to a perfect circle, the closer to 0 is. Eccentricity is always given as 3 decimal places. So we have the tens, hundredths, and the thousandths decimal place. So we always round to the thousands, 3 decimal places. There are also no units with eccentricity. If you don't round to the 3rd decimal place, or you put units, your answer is going to be wrong. So just remember that as you are doing your calculations for eccentricity later on.
Don't forget to listen to the earth. You just may